So, continuing with what we were discussing in the last lecture, that is Avrami kinetics, we had considered two cases, but first let me just write down two basic relationships. The fraction in alpha to beta transformation, the fraction transformed is given by 1 minus exponential minus the extended volume V beta E divided by the volume of the system, and the extended volume of the transformed beta was written as 4 pi by 3 integral 0 to t the nucleation rate times the radius of a nucleus nucleated at time tau cube d tau. And the two cases we had discussed were cases where nucleation rate was a constant. So, constant nucleation rate I, and hence I can be taken out of the integral. And in case 1 considered constant growth rate given by V, and therefore the size of the nuclei which nucleated at time tau would be at any time t was written as the growth rate times the instant of time t minus tau. Substituting this radius into this integral, taking this I out of the integral, we can then integrate to get the extended volume and then substitute the extended volume into the top equation, and which gave us the fraction beta transformed as 1 minus exponential minus pi by 3 I V cube t to power 4. We can lump all of these quantities which are a constant in one parameter k, and hence the relationship that was written turns out to be exponential minus k t to power 4. Similarly, case 2 was considered, and in the case of case 2, nucleation rate was parabolic. No, sorry, nucleation rate is still kept constant. We have parabolic growth rate. That is, the growth rate is proportional to the square root of time, and hence r tau in this case becomes a constant b times t minus tau to power half. From this, one got the function for fraction of beta transformed as a function of time as 1 minus exponential minus k t to power 2.5 or 5 by 2, where k in that case was 8 pi by 15 the nucleation rate times the constant b cubed. So, what we find is that we have different exponents of time depending on what model of growth rate one chooses, And of course, what model of growth rate one would choose would depend on the system, whether you have interface controlled or diffusion controlled here, as shown here. Similarly, one can look at couple of other cases. Here we had considered nucleation rate occurring throughout the transformation. There is a possibility where you would have most of the nucleation getting completed in the very early stages of transformation, and that can happen when site saturation takes place. Site saturation means sites for nucleation get completely exhausted. So let us take an extreme case where site saturation takes place at basically at the start of the transformation or time t equal to 0. And let us say that we have N0 nuclei per unit volume present at time t is equal to 0, and beyond this time there is no more nucleation is going to take place. Hence, all growth would take place for only those nuclei essentially which formed right at the start of the transformation. In this case, the extended volume would then become, or rather the extended volume would have to take this into account, that there is no nucleation occurring beyond time t is equal to 0, but we still have to choose what growth model to take. For example, suppose we consider a third case where we assume a constant growth. So, constant growth rate V, since all the nuclei have formed at time t is equal to 0, volume of any nucleus at any time t would simply be 4 pi by 3 R0 cube, where R0 is essentially the subscript 0 is designating all the nuclei which formed at time t equal to 0. The total extended volume would then, this volume of one nuclei multiplied by the total nuclei present in the system, and volume of the system we have been taking as V, and we have N0 nuclei per unit volume. Therefore, the total number of nuclei present at the start of the transformation is N0 times V multiplied by volume of each nucleus. This then becomes simply the extended volume. We substitute this extended volume into this exponential relationship to get fraction beta transformed as 1 minus exponential minus 4 pi by 3 N0 and inside here is R0 cube, and this R0 cube can be replaced by R0 is simply the growth rate times t, and hence R0 cube can be replaced by V cube t cube. So, in this expression then f beta is equal to 1 minus exponential 4 pi by 3 N0 V cube t cube. Here again you will see that one can take these terms in the circular brackets as a constant k, and this time we have fraction beta transformed as 1 minus exponential minus k t cube. Here now the exponent of time in this case is 3 as compared to the previous two cases where we had an exponent of time of 2.5 and exponent of time of 4. Let us consider one final case as well, and of course one can look at other cases as well, but here in this lecture I will just take one more case where the growth rate is parabolic. Now the extended volume would simply be N0V times 4 pi by 3 R naught cube, and R0 would be written as V T to power half. So it is following square root of time, or rather this should not be V at all, we can just put it by some constant B T to power half. Substituting this in R0, one will get N0V 4 pi by 3 B cube T to power 3 by 2, and from this now the fraction beta transformed at any instant of time t is given by f beta 1 minus exponential minus 4 pi by 3 n0 b cube t to power 3 by 2. Again we can lump all of these parameters as a constant k, and one will get f beta equals 1 minus exponential minus k t to power 1.5. So in these four cases that we have considered, we have got different exponents for t 1.5 all the way to 4. So there is a whole range of exponents we get, and we can try other combinations of nucleation rate and growth rate. For example, sometimes nucleation rate could be considered itself as an exponential function of time, so which could also be plugged in and one would get a somewhat different relationship. So in general then, the Avrami relationship could be written as f is equal to 1 minus exponential minus k t to power n. Now what kind of a function is this? If I plot this as f versus t, then of course the fraction transformed f will vary between 0 and 1. So this function is going to basically vary between 0 and 1 as time increases from 0, and one would get a curve, a typical curve like this, which is also called the sigmoidal curve. In fact, this is the same kind of curve we had got right when we had started discussing the kinetics of phase transformation, and I had shown you a simulation which of course did not assume any of those equations, but the simulation gave me the same kind of sigmoidal curve. And in fact, in that simulation, if you fitted that curve, one would get different values of n depending on what growth model one has taken and what nucleation model one has taken. Another thing about this function to note is that at t is equal to 0, the fraction transformed is 0 as expected, and as t tends to infinity, the fraction transformed tends to 1. And then this function can be examined for different values of n. So, for example, you will get a shape like this for n greater than 1. So, this is a shape corresponding to n greater than 1. What happens for, let us say, n less than or equal to 0? If I take n less than or equal to 0, this function, for n is equal to 0, this function would be a constant. So, it will have some constant value which essentially appears to mean that whatever has transformed at t is equal to 0 and then it remains fixed. So, that is kind of absurd. So, you can't have value in the Avrami parameter n to be 0, or in fact if n becomes less than 0, then this function would have a decreasing value that again will not make any sense, that without any transformation the fraction transformed is reducing. Hence, for n less than or equal to 0, this relationship has no meaning. Between n greater than 0 and less than 1, this function looks like a continuously decreasing rate of transformation, but it will still go from 0 to 1. Here, for n greater than 1, there is a kind of an incubation period before which any measurable transformation takes place. Then the transformation rate keeps increasing until it will reach a point where the transformation rate will start to reduce again, and as you can see towards the end, the transformation rate becomes very slow. It can be explained on the basis that initially very few nuclei are present and hence the rate is slow, and then large number of nucleation has occurred by this time and they are all growing, so the rate is going up, but towards the end now fraction of untransformed material has become less, and hence the number of nuclei that are new nuclei that are forming are also reduced, and therefore your transformation rate slows down. With these few comments, I'll basically look at this relationship and see how I can apply it. Suppose I had experimental data and I wanted to fit this relationship to experimental data, then how do I fit this equation to experimental data in order to determine k and n? And what is the purpose of that? Is that I have an experiment, I do an experiment in which I have measured fraction transformed as a function of time. I fit that data into this expression and try to find n and k, and interestingly the value of n would give me a clue as to what kind of a mechanism that may be operative. For example, if I get value of n close to 4, this tends to suggest that I have a constant nucleation rate, constant growth rate. If I had a value of n equal to 1.5 or close to that, then this may suggest that site saturation is taking place and the growth rate may be parabolic, but we cannot make this conclusion unambiguously, because there may be other processes that may be operating which may also lead to similar values of n, but this only would give us a clue as to what kind of mechanism of transformation that may be taking place, and one will have to generate more evidences from other kinds of experiments in order to finally make a conclusion as to the mechanism of phase transformation. So, let us look at this equation and how we can apply it to what kind of systems. First of all, we can apply this Avrami relationship. Well, this Avrami relationship can be applied to very large number of systems. It could be applied to polymorphic transformations, it could be applied to recrystallization, kinetics, it could be applied to some order disorder transformations, polymorphic transformation, for example, could be iron in the face centered cubic state, gamma iron transforming to alpha iron or the body centered cubic iron. Recrystallization kinetics, we deform a material and we anneal it. So, there is recovery, recrystallization and grain growth. So, one can look at the kinetics of those using this relationship. Order disorder transformation, an example of that could be a gold copper alloy, for example. There are other order disorder transformations as well. So, for example, this particular alloy gold copper Au3Cu at high temperature, this is disordered face centered cubic. This is at high temperature. This undergoes a transformation on lowering the temperature to ordered simple cubic. This is at low temperature. Disordered FCC implies basically that it is an face centered cubic structure where gold or the copper atoms can be at any of the lattice points, whether it is a face centered cubic or whether it is a face center lattice point or a corner lattice point of the cubic unit cell. But when it transforms to this ordered simple cubic, then copper atoms are at the corners of a cube and gold atoms reside at the face centers of the cube. So, even this can be analyzed with the Avrami relationship. Then you can have diffusional transformations. None of these actually require long range diffusion. So, when I talk about diffusional transformation, I am implying long range diffusion. In the case of diffusional transformation, we can look at steel or the iron carbon system. In the iron carbon system, gamma austenite can transform to ferrite, austenite can transform to pearlite, lamellae of ferrite and cementite. One can look at these transformations in the light of the Avrami relationship. So, just to quickly understand the diffusional transformation of austenite to ferrite and austenite to pearlite, you can see the iron carbon phase diagram here, and if I choose a steel with a hypoeutectoid composition, so less than 0.8% or 0.76% carbon, then the kind of microstructure I will get as I start to cool down from austenite region into this ferrite plus austenite. So, the ferrite will start to transform in a diffusional manner, and then finally going below the eutectoid line, the remaining austenite transforms to pearlite, and this is what is displayed in the microstructure here. So, there are pearlite islands in a ferrite matrix, and you can more clearly see the structure in a scanning electron microscopy image, and the pearlite can be even more clearly seen in an atomic force microscope image here, where the lamellae of ferrite and cementite are very clearly visible. So, whether it is austenite to ferrite transformation, one can study this. It is a diffusional transformation, one can study it from the perspective of the Avrami relationship and determine what the parameters n and k are experimentally, as we will soon see how. In these micrographs, one can also see that the ferrite is these dark regions all around, and inside here is pearlite. So, all this ferrite is actually heterogeneously nucleated onto the austenite grain boundary. So, austenite grain boundary are the sites for nucleation, and it could so happen in at least in some systems that you may end up getting site saturation. Similarly, if I take a hypereutectoid steel composition greater than the eutectoid 0.8% carbon, then in this case the microstructure one would get would be cementite all along the austenite boundaries and pearlite developing in the rest of the region. And finally, of more interest to us right now is the eutectoid composition itself, where all of austenite transforms to pearlite through the eutectoid reaction, gamma going to ferrite plus cementite, and the microstructure one would get would be pearlite everywhere. And one can design an experiment to experimentally investigate the kinetics of this particular transformation of austenite to pearlite. So, we start with a eutectoid steel, heat it up into the austenitic region as per the phase diagram, and then cool it just below the eutectoid temperature of 723 degrees centigrade. To do this, we have to do this very quickly. So, let us say our steel was kept at 850 degrees centigrade, it has to be cooled rapidly to let us say 700 degrees centigrade below the eutectoid temperature. It could be 650 degrees centigrade as well. In order to do this rapid cooling, one quenches the sample in a molten salt bath kept at the temperature of transformation, whether 700 degrees centigrade or 650 degrees centigrade or 680 degrees centigrade, at whatever temperature one wants to investigate this particular transformation of austenite going to pearlite alpha plus Fe3C. So, one will have to quench several samples, each sample being kept at different times in the salt bath. So, you keep it for certain amount of time in the salt bath and then quench it in water. The idea of that is that the remaining austenite, the untransformed austenite, is made to transform to martensite, which is a metastable phase in the steel system. So, then finally, the microstructure one would get at some time t, kept at some temperature capital T, the initial austenite grain boundaries, suppose these were my initial austenite boundaries, one will start to form pearlite at those boundaries, and rest of the untransformed austenite will be made to transform to martensite. So, I will have martensite and pearlite, one will take this sample, polish it, put it under a microscope, and then determine what is the volume fraction of perlite that is there. That can be determined by standard stereological technique of, for example, simple point counting, that you put a grid of points and count the number of points falling inside perlite. That number divided by the total number of points I have superimposed would give me an estimate of the volume fraction of perlite. So, what I will have in the end is F perlite versus time for some given transformation temperature T. So, I will have F1 T1, F2 T2, fraction transformed is F3 at time T3 and so on. Now, I take this data and then analyze it in terms of the Avrami relationship in order to find the parameters n and k. So, what do? I take this relationship f is equal to 1 minus exponential minus k t to power n. I rearrange the terms, write it as 1 minus f is equal to exponential minus k t to power n, take logs on both sides. So, I will have natural log 1 minus f equals minus k t to power n. Now, f is of course a fraction less than 1. So, 1 minus f would be less than 1. So, natural log of 1 minus f will be a negative number. So, what I do is I take this minus sign here and make this plus here. So, now what I have is positive values on both sides of this relationship. So, I can take logs again. So, natural log of minus natural log of 1 minus f would be equal to ln k plus n ln t. What was the purpose of doing this? Well, the purpose of this was to linearize the Avrami relation. Now, the left hand side, which is a function of two logs, is a linear relationship with log t. So, if I take that experimental data that I have and plot on the y axis ln minus ln 1 minus f versus ln t, if the data follows the Avrami relation, then the experimental data points must roughly fall on a straight line. I can put a best fit line through these data points. The slope of this line then would be from this linearized relation is simply n, and the intersection with the y axis would give me ln k. So, the intercept gives me log k, the slope gives me n. So, this way from experimental data I can easily determine the parameters n and k. I will stop here in this lecture, and in the next lecture we will take a very important topic where the from the Avrami relation how we can go to what is called as the time temperature transformation diagram. Thank you.